Algebra. Scope: manipulation of various algebraic expressions, equations in one and more variables, dealing with nonlinear equations, algebraic identities. Concept of variables: a variable is a placeholder which can be used in mathematical expressions. They are most often used for two purposes: in algebraic equations, to represent unknown quantities in known relationships. For example, Mary's age is 10 more than twice that of Jim's. We can represent the unknown Mary's age by x and Jim's age by y, and then the known relationship is x is equal to 2y plus 10. In algebraic identities, these are generalized relationships such as square root of x square is equal to mod x, which says for any number, if you square it and take the root, you get the absolute value back. So the variable acts like a true placeholder which may be replaced by any number. Basic rules of manipulation: when switching terms from one side to the other in an algebraic expression, plus becomes minus and vice versa. So example, x plus y is equal to 2z. So x is equal to 2z minus y. So y, when it goes to the right hand side, the sign before y plus became minus. When switching terms from one side to the other in an algebraic expression, into becomes divided by and vice versa. So 4 into x is equal to y plus 1 whole square, which gives x is equal to y plus 1 whole square by 4. You can add or subtract or multiply or divide both sides by the same amount. So x plus y is equal to 10z, which gives x plus y by 43 is equal to 10z by 43. You can take to the exponent or bring from the exponent as long as the base is the same. So x square plus 2 is equal to z, which gives 4 to the power of x square plus 2 is equal to 4 to the power of z. 2 to the power of 4x is equal to 8 to the power of y, which gives 2 to the power of 4x is equal to 2 to the power of 3y, which gives 4x is equal to 3y. It is important to note that all the operations above are possible not just with constants but also with variables themselves. So you can add x or multiply with y on both sides while maintaining the expression. But what you need to be very careful about is when dividing both sides by a variable. When you divide both sides by a variable or do operations like cancelling x on both sides, you implicitly assume that the variable cannot be equal to 0 as division by 0 is undefined. This is a concept which shows up very often on GMAT questions. Degree of an expression. The degree of an algebraic expression is defined as the highest power of the variables present in the expression. Degree 1 is linear, which is x plus y. Degree 2 quadratic, x square plus x plus 1. Degree 3 cubic, x cube plus x plus 2. Degree 4 biquadratic, x to the power of 4 plus x cube plus x plus 1. X plus y is the degree is 1. X cube plus x plus 2, the degree is 3. X square plus x plus 1, degree is 2. X to the power of 4 plus x cube plus x plus 1, degree is 4. Solving linear equations or equations of degree 1. Degree 1 equations or linear equations are equations in one or more variable such that degree of each variable is 1. Let us consider some special cases of linear equations. One variable. Such equations will always have a solution. General form is ax is equal to b and solution is x is equal to b by a. One equation in two variables. This is one equation in two variables. This is not enough to determine x and y uniquely. So there can be infinitely many solutions for one equation in two variables. Two equations in two variables. If you have a linear equation in two variables, you need at least two equations to solve for both variables. The general form is ax plus by is equal to c, dx plus ey is equal to f. If a by d is equal to b by e is equal to c by f, then there are infinite solutions. Any point satisfying one equation will always satisfy the second. If a by d is equal to b by e not equal to c by f, then there is no such x and y which will satisfy both equations. So no solution. In all other cases, solving the equations is straightforward. Multiply equation 2 by a by d and subtract from 1. More than two equations in two variables. Pick any two equations and try to solve them. Case 1 would be no solution. Then there is no solution for bigger set. Case 2 is unique solution. Substitute in other equations to see if the solution works for all others. Next, case 3 is infinite solutions. Out of the two equations you picked, replace any one with an unpicked equation and repeat. More than two variables. This is not a case that will be encountered often on the GMAT, but in general, for n variables, you will need at least n equations to get a unique solution. Sometimes you can assign unique values to a subset of variables using less than n equations using a small trick. For example, consider the equations x plus 2y plus 5z is equal to 20, x plus 4y plus 10z is equal to 40, uh, x plus 2y plus 5z. In this case, you can treat 2y plus z as a single variable to get x plus of 2y plus 5z is equal to 20. X plus 2 into 2y plus 5z is equal to 40. So this can be solved to get x is equal to 0 and 2y plus 5z is equal to 20. So there's a common misconception that you need n equations to solve n variables. This is not true. Solving quadratic equations or equations of degree 2. The general form of a quadratic equation is ax squared plus bx plus c is equal to 0. The equation has no solution if b square is less than 4ac. The equation has exactly one solution if b square is equal to 4ac. The equation has two solutions given by minus b plus or minus square root of b square minus 4ac by 2a if b square is greater than 4ac. So the sum of roots is minus b by a and the product of roots is c by a. If the roots are r1 and r2, the equation can be written as x minus r1 into x minus r2 is equal to 0. A quick way to solve a quadratic without the above formula is to factorize it. So divide throughout by coefficient of x squared to put it in the form x squared plus dx plus e is equal to 0, which gives x minus f into x minus g is equal to 0. X squared plus 11x plus 30 is equal to x squared plus 5x plus 6x plus 30 is equal to x into x plus 5 plus 6 into x plus 5. So the sum in this equation x squared plus 11x plus 30 is the sum is minus 11 and the product is 30. So at the end we get x plus 5 into x plus 6. Solving equations with degree greater than 2. You will never be asked to solve higher degree equations except in some cases where using simple tricks these equations can either be factorized or be reduced to a lower degree or both. What you need to note is that an equation of degree n has at most n unique solutions. Factorization. This is the easiest approach to solving higher degree equations. Though there is no general rule to do this, generally a knowledge of algebraic identities helps. The basic idea is that if you can write an equation in the form a into b into c is equal to 0, where each of a, b, c are algebraic expressions. Once this is done, the solution is obtained by equating each of a, b, c to 0 one by one. So x cubed plus 11x squared plus 30x is equal to 0, which gives x into x squared plus 11x plus 30 is equal to 0, which has x into x plus 5 into x plus 6 is equal to 0, which is x is equal to 0 comma minus 5 comma minus 6. Reducing to lower degree. This is useful sometimes when it is easy to see that a simple variable substitution can reduce the degree. So for example, we have x power 6 minus 3x cube plus 2 is equal to 0. Here, let y is equal to x cube. Y square minus 3y plus 2 is equal to 0, which gives y minus 2 into y minus 1 is equal to 0. So the solution is y is equal to 1 comma 2, or x cube is equal to 1 comma 2, or x is equal to 1 comma cube root of 3. Other tricks, uh, sometimes we are given conditions such as the variables being integers, which make the solutions much easier to find. When we know that the solutions are integral, oftentimes solutions are easy to find using just brute force. Example, a square plus b square is equal to 116, and we know a, b are integers such that a less than b. We can solve this by testing values of a and checking if we can find b. So a is equal to 1, b is equal to root 115, not integer. A equal to 2, b equal to root 112, not integer. A equal to 3, b equal to root 107, not integer. A equal to 4, b is equal to root 100 is equal to 10. A is equal to 5, b is equal to root 91, not integer. A equal to 6, b is equal to root 80, not integer. A is equal to 7, b is equal to root 67, not integer. A equal to 8, b is equal to root 52, less than a. So the answer is 4 comma 10. Let us look at very useful algebraic identities. These can be useful in simplifying and solving a lot of questions. So x plus y whole square is equal to x square plus y square plus 2xy. X minus y whole square is equal to x square plus y square minus 2xy. X square minus y square is equal to x plus y into x minus y. X plus y whole square minus x minus y whole square is equal to 4xy. X plus y plus z whole square is equal to x square plus y square plus z square plus 2 into xy plus yz plus zx. X cube plus y cube is equal to x x cube plus y cube is equal to x plus y into x square plus y square minus xy. X cube minus y cube is equal to x minus y into x square plus y square plus xy.